right, let's look at this. So think about how I actually have it over here. We can mess with it. Well, actually, let's go ahead and, I don't know if you're going to be able to see this. I'm making Jennifer move the camera. Sorry, Jennifer.
You're good.
All right, I'll bring this up higher. Did you get that on tape?
Yes.
All right. Hold the stand. I tell you what, I think we'll worry about that demo later. Never mind. Sorry. Sorry. All right. We're just going to have to imagine stuff. We're going to have to imagine something. All right. So when I pull on the string from if I pull here, what happens to the load?
It goes up, right?
Okay, it rises. How is this different than the previous case?
You decrease your amount for the effort force.
Before we get to the forces, do you think this moves the same amount as you pull? Here's one way of thinking about it. Both sides, you're going to be taking up length on both sides. So 1 foot here is going to be shared between these two. So you're going to share half a foot on each side. So this thing's going to move up half a foot.
For every 1 foot you pull.
For every 1 foot you pull. Okay. So it turns out the way this works is you're pulling with some force. That force is distributed. That force is there's a tension in this rope everywhere that's equal to your effort force. Is everybody with me on that? So the way of thinking about a string that you're applying a force to, if I've got F pulling here, I have 2F here. I've got an F here and an F here. I've got force pulling up. So both of these strings are pulling up on this pulley with the force that I'm applying.
So what you're saying is basically combined and make it equal, because the amount of effort, you said that if you pull the effort force, you move 1 foot. You said that amount of effort is being transferred over to equal parts, right? Like you say, maybe half here and half there. So combined it equals.
Well, the force times, so I think you may be getting to the idea of work. There's actually twice as much force pulling up here.
Okay.
Because that rope is up top and pulled in, so that is bearing some of the load.
That's actually a good way of looking at it. I'm pulling here, and actually the ceiling's also pulling with the same force. So the load is actually being pulled up by two times the force. But here's the thing, it's only moving half as far.
But it's still less.
So it's the same amount of energy. The amount of work I put in here is equal to the amount of work done on the
So
load.
if you're by yourself, that would be energy efficient for you. But if you had an elephant helping, the first one would get your job done.
Well, it's interesting the way you put that. Is it more energy efficient?
Same amount of energy.
It's the same amount of energy, because you have to go twice as far. You have less force, but you got to go twice as far to lift the same distance. So that's what I meant by you're not getting something for nothing. We are winning because it's less force, and that's what we want. But we're actually putting the same amount of energy in as we did before. Okay, so you have to pull with the same force over a longer distance. I mean, pull with a lower force over a longer distance.
So, sorry to stop us, I know we'll move on with
No,
energy.
I don't want to move on.
So
You want
force
questions?
then and energy are really not synonymous
No, force and energy are not the
at
same
all,
thing.
right? And so how are they related? Is what I'm trying to sort out.
Okay,
So
energy. So
W being E in the sense of energy.
okay,
right?
that's confusing. I'm being confusing. So you're right. The way force and energy are related. You're changing.
Because
Force
when
and
I
energy
think of it in a human sense, not a physics sense, if I'm applying less force, then I'm using less energy.
But you're doing it through a longer distance. So the energy
So
the
does that
energy you
mean-
exert is the force times the distance. So when
Okay.
I say I
But I'm
apply,
less tired in this example than it would be in the first one, but that's not the energy we're talking about.
Right, that kind of has to do with the efficiency, how efficient a human being is.
Right, that's what I meant by efficiency, but in the
Yeah.
sense of physics, it's
Yeah.
not efficient.
That's correct.
Okay.
I mean, it's the idea of, so let's go to another example. Let's go to this example, okay? Here's another example. It's actually the same idea. Let's say, if you wanted to get, let's say that this is a car you're pushing up a hill. Do you want it to be a shallow slope or a steep slope?
Shallow.
Okay, but what does that mean? If it's a shallow slope, how are you? Yeah, you're going to have to go farther. Your force is less, but you're going to have to push it farther. Okay? So the energy you put into it actually, technically, for a human being, it's not necessarily the case because we have a certain range of forces where we can operate comfortably. But in terms of the physics, it's the same amount of energy. Energy, you're going to change this if you move this load up this ramp, you're going to change its energy the same amount, whether or not you're going to change its potential energy the same amount, whether it's a shallow slope or a steep slope. But it's easier for you with a shallow slope because you have less force over a longer distance. Okay? Yes?
So back to the pulley. So what would be the mechanical advantage of that pulley system with the 2 pulleys?
2. I'm sorry, I should just answer the question. Oh, wow, where am I going? What would the mechanical advantage be?
So I don't know whether it would be 2 or 1/2.
It's the load over the effort.
But I don't know what the load is there. Is the load?
Okay, okay, right. So in equilibrium here, if I'm just holding this,
Yeah.
I'm applying a force here. There would be twice that force pulling up, which means this load would be equal to twice the force that I'm pulling with. So your load is twice your effort in this case.
So it's 2 over 1.
Is it simply counting the number of pulleys?
Simply counting the number of strings. That's how you figure out the mechanical advantage of a pulley system. You
Yeah,
look
so
on,
what strings are you counting then?
okay, the way to look on a pulley system is look at the load and how many strings are sort of directly pulling on the load. I mean, immediately next to the load. Okay?
So 1, 2.
1, 2.
But would the work being accomplished be half of the previous example?
Yeah. Well, for every foot
this
you
is only
pull,
going a
it
half.
goes a half, 6 inches up.
So the work
Would be less.
is.
Well, the work is half.
Less the first time.
The work is half. The work is half per, but you have twice the force. So the total energy. So let's look at both cases. I hope this is useful. I don't want to be getting to the nitty gritty of this. I'll go through this. I think this is fun stuff. In this case, let's just do the same thing in both cases. I go 1 foot.
And
That
it
goes
lifts
up
1
1
foot.
foot.
All right.
So the work being accomplished.
It's basically balanced. So
This amount of, I put this much work in that. Okay, so look at it this way. There's a force here, and it's the same force here, correct? So force times a distance, force times a distance. All right? That same force times a distance.
But work is force times distance.
All right? In this case, let's go 1 foot. 1 foot with the force F. All right? Half a foot, but I've got 2F.
So it's equal.
Yeah.
technically it
But it-
balances
but
out.
it's only
But
going-
it's just
The energy is the
spread
same.
out. Okay.
The energy is the same on both sides. The force is amplified, and the distance is halved. You do twice as much force, half the distance on the load side. And it's kind of the same thing for this case. I mean, you're doing less force. The slope determines how much force you're going to apply. Shallow slope, less force, more distance. And in a perfect world, and what I mean by in a perfect world is there's no friction. Some of the work that you're going to do is going to go into friction in this case. But in a perfect world, your force times the distance, no matter what the slope, is always going to equal to the however you change the potential energy of this thing. Okay.
With the pulley too, I did a scavenger hunt with my kids. So they went to 6 different stations that I had to sort out which simple machine to use. And so when we looked at the pulley, they hung the string over the rod that the pulley was being suspended from and pulled, and there was a lot more friction. So they determined that a pulley reduces friction when they're trying to raise something.
Right, that's another thing.
It's so advantageous about it.
Right, that's another thing that it's doing. You're bringing up another point that I should point out, is that the mechanical advantage, I was asked what the mechanical advantage of this system is. Ideally, it's 2. In reality, it's going to be less than 2, because some of the force you're pulling on, some of the force that you're applying here is going to go into friction, is going to be being imposed by the friction in the pulleys, okay? The friction of the rope. So ideally, it's got a mechanical advantage of 2. This is actually another way that you could see this. This is actually the same. This is the way you could hook 2 pulleys together in a clever way to get a mechanical advantage of 2. So this string comes around and hooks back up to the first pulley, but you're getting 2 forces up from one force over here. Now you can string these together. I promise I'm not going to knock anything over this time. But this one that Alice very carefully put together has got 6. Okay? There's 6 strings pulling up this side. So when I pull on this side, this is moving up 1/6 the distance that I'm pulling down. Okay? And in principle, did I just mess it up? I just messed it up. In principle, you could get close to 6 times the force amplification, but I think Alice found, where is Alice? Alice here? Alice found that it was actually significantly less than 6 because of all the friction. This is a pretty, you can hear it, it's squeaking. It's not a perfect pulley, so you're not getting all that force amplification out of this. It's definitely, there's a lot of mechanical advantage there, but it's not 6. It's a lot less than 6. All right, let's talk about the lever. So let's apply some of the ideas we've just gone through to a lever. How does this work in terms of energy, force, and distance you're moving? So if, the work you're doing to an object is the force times the distance, right?